Welcome to Chapter 2 of ExHAC, Defining the Hazard. Let's start this journey by discussing what is a hazardous area classification and why do we need it. A classification design describes the probability and the location where an explosion hazard will exist. It is used to specify explosion-rated electrical, mechanical, and instrumentation equipment. It also influences the material and wiring methods used to construct a facility, and, most importantly, it defines the safe work practices used in that facility. In this chapter, we are going to discuss a variety of situations where an explosion hazard may exist. These situations will warrant a classification design. We will also introduce you to the people who will rely on this information to make explosion safety-related decisions. Let's start with the fire triangle. It helps us understand how a classification design relates to explosion safety. For a fire or explosion to occur, 3 elements are required: oxygen, a fuel source, and an ignition or heat source. The air we breathe is 21% oxygen, so by default, one side of the triangle is always complete. The fuel side of a triangle is what we look at when we perform a classification design. We want to understand the nature of the explosive hazard so we can take the necessary precautions to prevent the ignition and heat side of the triangle from being completed. Let's look at a variety of situations where an explosion hazard may exist. Many common manufacturing processes use flammable materials in their process. Examples include spray paint, distillation, solvents, and dipping applications. Perhaps the hazardous area may be a small part of a larger process. It still requires evaluation to ensure that no ignition sources are placed within the vicinity of the hazardous area. In chemical manufacturing operations, a greater portion of the process equipment may handle flammable gases and liquids. The classification surrounding individual release sources will merge to create an overall classified area that may encompass entire buildings or the plot extent. Many processes use a variety of flammable materials, each with their own unique explosion hazard properties. Knowing these properties and understanding their release characteristics is an important consideration. Oil and gas facilities incorporate hazardous locations. The process may be very simple, with only a few pieces of equipment, or it could be a large offshore drilling and production platform where the consequences of a release could be catastrophic. Refineries and petrochemical facilities present even greater challenges to explosion safety. Large quantities of flammable materials handled at high temperatures and pressures will warrant very large classified extents. Coupled with a large number of potential ignition sources, including unprotected fire heaters and vehicle traffic, a refinery classification can be a difficult challenge. Another industry sector of the economy where large quantities of flammable materials are handled are pipeline utility and fuel transportation applications. Many of these facilities handle natural gas at very high pressures or as liquids that have unique release characteristics. A liquefied natural gas release will expand to 500 times the liquid volume as it approaches ambient temperatures. A very small leak can create a very large hazard. Many biological processes can create a flammable atmosphere as a byproduct. Wastewater treatment plants are a great example. They produce large quantities of biogas from their anaerobic digestion of sewage. Biogas is explosive, and process equipment handling biogas will warrant a classification. As we move towards a carbon-free economy, hydrogen will play a larger role in our energy portfolio. Hydrogen is a very light gas that is difficult to contain and is prone to leakage. It also has a very large explosive range. This requires all equipment handling hydrogen be properly classified. Given that our process handles flammable materials, the next question we must ask is, Does my process leak? Most processes are well contained and do not leak. However diligent we may be, it is expected that minor releases will occur. Such releases, intentional or unintentional, pose an explosion hazard. Here we can see a variety of release scenarios using a non-dispersive or NDIR infrared camera. An NDIR camera can see hydrocarbon releases because hydrocarbons absorb infrared energy when in a vapor state. The videos you see here are from a plant NDIR scans in operating facilities. On the left is a valve stem release. Equipment with moving parts in contact with process fluids will wear over time. The reduced tolerance allows flammable material to be released. We are unlikely to shut down a plant to repair such a small release. Instead, we classify the area surrounding the release and restrict ignition sources in the area. Here we see a leak from an improperly installed needle valve. The leak remained undiscovered from the time the plant was first commissioned. Here we see a sample valve that was not fully closed after a sample was taken. In this example, we can see flammable emissions from the top of a storage tank. A process upset caused the vapor recovery system to shut down for a short period of time. Flammable vapors from the tank were released to atmosphere until the process condition could be corrected. Pumps can be a release source. Pump seals become worn over time, allowing process fluids to be released. Pump seal technology is a consideration. This brings us to the question, what is the probability of a component leak? There are several factors that influence the probability of a release. On average, facilities handling flammable gases will leak more than facilities handling flammable liquids. Plant equipment subject to wide temperature swings will also leak more. Plant maintenance practices are also a consideration. To answer this question, let's look at some typical probabilities associated with some common release sources. We will rate them on their probability of being a release source, relative to each other.
Take a look at these large pipes. The probability of a large pipe leaking is very low. Statistically, we can expect roughly one minor leak per year for every 100,000 meters of large piping. The probability of a major leak is even lower. All welded piping is not considered a leak source for the purposes of a classification design. Small pipes will leak more than large pipes. A 25 millimeter pipe is 10 times more likely to leak than a 250 millimeter pipe. Statistically, we can expect roughly one minor leak per year for every 10,000 meters of small piping. The probability of a small pipe being a leak source is very low. Most leaks occur at the connection points. This is where temperature cycling and piping movement over time can lead to a failure in gasket materials that seal the connections. The probability of flange leaks is a function of the operating conditions and gasket materials that have been used. Statistically, 1 in 1,000 flange connections will develop a minor leak in any given year. Consider this a medium likelihood. Valves that incorporate moving parts will wear with time. The rate of wear is service dependent. Statistically, 1 in 1,000 valves will develop a minor leak in any given year. 1 in 10,000 will develop a major leak. Consider this a medium likelihood. Pumps are roughly 3 times more likely to be a leak source than a valve. This is dependent on the pump service and the pump seal technology. Compressors and gas service will have an even higher probability. Consider the likelihood of a pump or compressor release as a medium to high. By far, the most likely components to leak are small bore connections on instrument tubing and sensor devices. Roughly 5 in 1,000 will leak each year. The likelihood will increase further if these components are subject to vibration from mechanical loads on equipment packages. Fluid transfer operations are another source of release. These are intentional releases that must be factored into a classification design. Atmospheric vents are another common source of release. Many tank applications incorporate a vent to the atmosphere, regulating pressure inside the tank during filling operations. Flammable vapors will be discharged into the atmosphere as the tank is being filled. This is a normal process that must be incorporated into a classification design.
Other common sources of release in many processes include condensate drains and sample points that open the process to atmosphere, instrument manifold vents, and filter vessels that are opened for routine maintenance while the plant is in operation are another example. Pressure relief devices that protect process equipment against overpressure may also release flammable materials to atmosphere for brief periods of time. Drains and enclosed sumps may also contain flammables and must be classified for this possibility. The hazard often extends below grade in many situations.
So how do we convey the probability of a flammable atmosphere being present to others who might need this information? We do this in the context of a hazardous area classification design. It defines the degree and extent of the explosion hazards that exist in a facility. It provides the necessary information for specifying explosion-protected equipment and ventilation design parameters. A classification design is required for all situations where there may be a flammable atmosphere in normal operation. It's required by national regulation in most jurisdictions. A classification design must be clear in intent, provide all necessary information, and be documented in a format readily understood by all parties. Many people will use this information to make explosion safety-related decisions. They include engineers. Engineers and designers require this information to specify equipment. It will impact the product standards and installation codes that apply to a project, as well as influencing the ventilation design of enclosed areas. Often the information is needed early in a project to specify long lead equipment items. Equipment suppliers will need this information to select explosion-rated components for their assemblies. It impacts the certification requirements for the equipment. Installers also need this information to select materials and determine the installation codes that will apply. This impacts the selection of wiring methods and where electrical sealing may be required.
Inspectors will use this information to verify the certifications on equipment, as well as to determine if an installation is code compliant.
And the group most impacted by classification design, operations. Operations and maintenance activities in classified areas require additional safety precautions to ensure worker safety. This may include the need for hot work permits and other procedures to restrict ignition sources in classified areas. Knowing where the hazard exists is essential for implementing a safe work practice.
To satisfy the information requirements of this diverse group, we need to ensure that our design documents 4 items. 1. The zone classification. This defines the probability of an explosive atmosphere being present in normal operation. 2. The extent of the zone. This is defined as the distance from the source of release to where an explosion hazard is deemed negligible. 3. The group classification of flammable materials. This impacts electrical equipment selection and wiring design. 4. The auto-ignition temperatures of flammable materials. This defines the maximum surface operating temperature limits for equipment. To help us perform a classification design, the IEC has published a standard. The IEC 60079-10-1 standard addresses the classification design of areas where an explosive gas atmosphere may exist. The standard is used worldwide to classify facilities using the zone system of classification. This course and the ExHAC application is based on the 3.0 edition of the standard. We've integrated the 3.0 edition of the standard into our course for your reference. Click the link below to see sections of the document as we discuss various concepts throughout our course. The complete document can be accessed from the link in the course player.
The ExHAC software application supports the assessment methods described in the IEC standard. It simplifies the task of collecting and analyzing data required for an assessment. The easy-to-use interface provides access to a variety of software tools needed to perform an analysis. The ExHAC application modules include:
the FMA Module allows you to assess the properties of flammable gases and vapors. The module incorporates select data from ISO IEC 80079-20-1 for many common flammable compounds. You can also configure custom compounds for analysis using data from the sources you define. The application can also analyze mixtures of flammable materials to determine the key parameters required for a classification design. The ExHAC SOR module allows you to configure a source of release sources for analysis. The application can simulate both gas and evaporative pool releases using formulae defined in the IEC standard. The ExHAC Enclosure Module allows you to configure an enclosure surrounding a release source. The application supports both forced ventilated and naturally ventilated applications. The ExHAC module takes the data from the FMA, SOR, and Enclosure module and predicts the zone classification and extent. It permits a variety of what-if release scenarios to be simulated. This helps in creating a good design. The ExHAC application is self-documenting. It allows you to organize classification data from multiple projects in an easy-to-read report format based on IEC standards. A detailed record of all calculation data used in the assessment is provided in a separate report. The information supports the development of your hazardous area classification plot plan and cross-section details. This gives you a fully documented classification design that can be maintained over the life of a facility.
I want to pause here and discuss the issue of competence. Before you certify that design, be sure that you understand the basic scientific principles of release behavior and recognize the benefits of operations experience. In the remaining chapters of this course, we will be discussing both scientific principles and other considerations needed for a good design. We will discuss the properties of flammable gases and liquids, their release behavior, and how a hazard can be mitigated by area ventilation. We will discuss the objectives of the IEC standard, and we will show you how to use the ExHAC application to assess a variety of situations. Now, what I want to say here is that ExHAC is a tool. It does not provide a definitive answer. Sound engineering judgment must be applied to every situation. We will discuss many of the design considerations throughout our course. We will start you on your journey towards competence. I encourage you to consider becoming an IEC EX COPC certified engineer in hazardous area classification design. The IEC certificate of personnel competence provides third-party verification of your skill set and allows others to verify your qualifications. For more information on the IEC EX COPC program, please visit the IEC website at the following link.